Hey, well, thank you, Scott. Just let me get the slides here. This should be okay.
Yes.
And I'll just get the pointer. There we go. So thank you, Scott, and good morning to all our colleagues in Argentina. It's a great pleasure to speak to all you people working in combined cycle HRSG plants in Argentina. It's a few years since I was down there and talking to some of you. So what we thought we'd do is we'd cover two main areas that Bob and I cover when we run HRSG meetings, either forums or other meetings around the world. And so what I'm going to do here is include some of the latest international statistics, specifically on those items of HRSG that are influenced by the cycle chemistry control. And so we'll just get going here. We've got to move this on. And so what we wanted to do first of all was just indicate that the Bob and I run these HRSG meetings. We run one in Australia every year in November, and it's the Australasian Boiler and HRSG User Group. We run the European HRSG Forum, which last year and next year are in Italy near to Florence. And we also run the Film Forming Substances International Conference. That was also in Italy this year. And most recently, the HRSG Forum has gone live, and that was in Atlanta in June. And Bob can tell you where it's going to be next year. And move on. So as Scott had indicated, what we want to do in this first session, talk about the damage and the failure mechanisms that are influenced by the cycle chemistry on an HRSG plant. And so I've tried to summarize the main ones right here, and we'll talk about each of them. So first of all, of course, are the tube failures that take place. And there are two main tube failures that we see all over the world. This one is flow accelerated corrosion, FAC for short. This is the leading HRSG tube failure mechanism, and we'll talk a little bit about that later. The other one is under deposit corrosion. We call this UDC, and this will also be discussed later. Mainly, we're talking here about hydrogen damage, and unfortunately, this seems to be increasing around the world. The second major area are the corrosion products. This is basically iron, total amount of iron that's transported from having inadequate feed water and in the lower pressure circuits of the HRSGs. And this, as you'll see a little later, is the leading chemistry factor, which is not addressed properly. And as a result, this ends up with deposition in the HRSG evaporator, which is one of the precursors for the under deposit corrosion mechanism. And these are exacerbated, increased, if you have an air-cooled condenser in the cycle. If the chemistry isn't correct on a plant with air-cooled condenser, you get very high levels of iron being transported. And then, although it's not in the HRSG, the other combined cycle mechanism that's important is in the steam turbine, and this is in the phase transition zone of the low pressure turbine, and we'll talk just a little bit about that. So this is what we're going to talk about for half an hour, and then half an hour, 40 minutes, we'll open it up for questions, and then move on to Bob's part. I have to click this each time. And so here's just an indication of the damage that occurs in the steam turbine. I just show this because I'm going to deal with the tube failure mechanisms in detail. The two main ones that take place are corrosion fatigue of blades and discs in the phase transition zone of the low pressure, which I'll explain what that is, and stress corrosion cracking in the discs of these. And you'll see some of the pictures here. I'll talk about a few of these in a little bit more detail. So what we've come to recognize over the years of conducting a large number of assessments in combined cycle plants and in conventional plants, actually now over 270 plants worldwide. I'll show you the data from this a little later. And it confirms that all of this failure and damage that you've just seen can be related directly to plants operating with what we call repeat cycle chemistry situations. There's basically 9 of them. I'm going to highlight some of these for you, but these are areas where plants are not addressing the chemistry in an optimum fashion, and I'll talk about each one as we go through here. So let's provide 3 examples. The first example is going to be on hydrogen damage. This is an under deposit corrosion mechanism, and this is basically because the damage takes place under a heavy deposit on the HP evaporator tubing. And there have been multiples already just this year of this mechanism, and it's becoming very important. It's a little bit distressing because we understand pretty much everything about hydrogen damage. So these are some of the examples that we have collected. So here you can see an HP evaporator tube, and you can see some very heavy deposits, internal deposits, and some quite serious corrosion just taking place here. When we look at the inside surfaces, you see, expect to see heavy deposits like this. You cannot have hydrogen damage or under deposit corrosion unless you have these heavy deposits. The failures that occur are usually similar to this, like a little window or a thick edge failure takes place. And this is a result of having this corrosion take place. You can see the corrosion here eating its way through the wall of the HP evaporator. And if we look at detail along this interface here between the corrosion and the metal, you'll see this light area here, which is the chloride, and the chloride is concentrated at the bottom of these deposits. It can only concentrate at the bottom of the deposits. And so this is very important. Sometimes we can't analyze this, but we know that it's there because of the mechanism. And so these are some of the typical repeat cycle chemistry situations which lead to hydrogen damage. These are the things that you need to look for to see if hydrogen damage is going to be a possibility in your HRSG. The main one I've already mentioned is excessive corrosion products. This is the total amount of iron that moves from other places in the cycle, moves from the lower pressure cycles, the low pressure evaporator, low pressure economizer, IP or HP economizer, and deposits out in the HP evaporator. And most often you can see that these levels of iron exceed the local guideline values. And I'll show you the guideline values in a minute. Sometimes these corrosion products are not measured properly, and sometimes plants only measure the soluble part of the corrosion product. So that doesn't measure the total amount of corrosion products that are being transported. So these corrosion products, they flow into the HP evaporator, and they form deposits on the surface. And most often plants have not taken samples of the HP evaporator to be able to identify whether those deposits are great enough to cause hydrogen damage to take place. And there's a particular guideline for that, which I'll show you. And the other main aspect, the third part of hydrogen damage, is that there has to be some contaminant enter into the cycle. Usually in the form of chloride or seawater in seawater cool plants. And these contaminant levels are allowed to exceed the shutdown limit or the action level, the chemistry action level or the chemistry shutdown limit. And so these are the main features: increased corrosion products, increased levels of deposits on the internal surfaces, and contaminant ingress. And so let's have a look at each one of these. This is a table taken from the IAPS guideline that you can get freely available. And so we have developed a series of guidance for the amount of iron. And so when you have a combined cycle plant operating on AVT, say, then you want that total iron level to be less than about 2 ppb, 2 micrograms per kilogram, or 2 ppb, and that would be a good target to aim for. In the drums themselves, in the HRSG evaporator drums, on any of the treatments, we'd want that total iron to be less than 5 ppb. And if you have an air-cooled condenser, we'd want the achievable level for iron is if you have a filter, usually we like a 5 micron absolute filter. We want it to be less than 5 micrograms. And so these are good guidance levels for you to aim for. And we know that if these are exceeded, the amount of deposits will actually increase. And go to the next slide. So we're working on a new understanding of monitoring iron using proxy methods, using turbidity or particulate analyzers. And you can see here this blue line here is the record of the total amount of iron flowing into the economizer as a function of time. So you have turbidity of this axis, and then you can translate this turbidity into the amount of iron, which we see right here. And what you want to do then is to take this trace and to put it onto the IAPS decay map. This is the IAPS decay map. So this shows iron up this vertical axis here, and this shows the time from the startup. And here's that trace that I just showed you down at the bottom. You ideally want it to be in the green area at the bottom. Green area indicates that the plant is operating with optimum chemistry control during operation and has reasonable good shutdown conditions. Contrasted by that, if you're in the red area, that's poor operational chemistry and shutdown chemistry. So this tells you, this trace superimposed on this decay map provides you an indicator of whether the chemistry is okay or not. And this trace here is from a good combined cycle plant in Denmark that we monitored. And you contrast that by something like this. This is an example from a plant with non-optimum shutdown conditions. And here you can see that this trace is not in the green area and has a number of peaks like this. And each time these peaks each time the trace shows a peak like this, it means there's a high level of iron, as you can see over here, that's going to go into the unit and therefore increase the deposit. So this is a very powerful new tool that we're working on. We have already published a white paper on it. Our IAPS has published a white paper, and we'll be publishing a final guidance document probably next year. So the second area is to make sure that you have the right level of deposits on the internal surfaces of the HP evaporator. And again, this is this is from the IAPS guidance document for those deposits. Again, you can get freely available, and so you have up the vertical axis the deposit loading on the internal surface in grams per foot squared or milligrams per centimeter squared. And where you want to be is in this as a function of pressure, and where you want to be is in this green area right here. And you know that that if you take a sample and you measure the deposit loading and it's in the green area, then there's no possibility of you having hydrogen damage. But if, for instance, you take it in the top of the yellow or in the red, these are very heavy deposits, and that means that there's a possibility that if you have some contaminant ingress, you can get hydrogen damage. So these are two examples. This one and this one on either side are two examples that we just looked at. So you can see it in both cases here that the deposit, so here is the deposit on the internal surface right here for this tube, and here's the deposit on this tube right here, and you can see that these levels are very high, 65 milligrams per centimeter squared and 80. And so if you look at this, the deposit map, you'll see that these are right at the top of the red band. So this is a very dangerous situation for those particular plants, and they know that if you have some contaminant ingress, then they'll almost certainly result in hydrogen damage, in a failure. So the idea is to take these samples at regular intervals so you can make sure that the deposits are not building up on the internal surface of the tubes. So that was the first example. The second example is flow accelerated corrosion, which, as I mentioned before, is the most frequent damage mechanism in HRSGs worldwide, and we still see many of these every year. I'll just put to get this to work. So I'm going to show you some examples of FAC in combined cycle plants. Basically, over the last 10 or 15 years, we've not seen any new locations or situations of where FAC can take place. But one of the common features is that plants and operators tend to mix up the difference between single phase and two-phase FAC. In a combined cycle in HRSG, you can have both single phase in 100% liquid or water and two-phase in two-phase mixtures of steam and water. And these are still occurring worldwide and not being identified properly. So one of the things I wanted to show you was some examples on how to make that distinction. And the importance is that each one of these mechanisms, single and two-phase, are dealt with differently from a chemistry point of view. You can switch them off by different aspects of the chemistry. So it's important that you identify exactly which mechanism you have. So this just provides you a little bit of statistics. You can see here, which will become clearer on the next slide. This is two-phase. This is two-phase FAC at the top of the LP evaporator. And FAC, as it says here, continues to occur and represents more than 40% of all the tube failures in HRSGs, despite a lot of R&D since the 1960s. And so down here, you can see a little explanation of how FAC takes place. And if you want to see it in detail, you can see the latest paper. This is the latest paper on FAC. And Scott has these papers, so if anybody wants them, he can tell you at the end here of how you can acquire these. But this is the latest understanding of FAC, of how it takes place on a carbon steel material with fluid flow. This fluid flow, of course, could be 100% liquid, water, or it can be a mixture of the two. And FAC is simply a removal of this oxide from the surface at a faster rate than the oxide grows on this surface right here. And I'm not going to go into too much more detail about it, but this is increased by the turbulence, by the bends at the top of the low pressure evaporator, typically, or some geometrical feature helps to remove these particles from the surface. And that's essentially what FAC is. Now here's two examples. So this is an example of single phase FAC. At the bottom here, an HP economizer. This is the inlet header at the bottom, and the geometrical feature here is this bend right here. Most typically, single phase FAC takes place in combined cycle plants which operate on AVTR. That means that a reducing agent, or you might call it an oxygen scavenger, are added to the chemistry. And this is the typical appearance that you see here of single phase FAC. It looks like, we most often say it looks like an orange peel, the surface of an orange. And you can see on this one here, just around this bend here, which has produced the geometrical feature, you get this appearance of this single phase FAC damage. And contrast that with this example, which is two-phase FAC in LP evaporator. Usually at the top of the LP evaporator, where there's a mixture of steam and water, and here you can see this black shiny appearance. This is the very typical appearance of two-phase FAC. It's always black and shiny like this, and just about where it's starting, which would be down here somewhere, you can see these little, what we call these dimples. These are dimples of FAC, and this is very characteristic. You do not see these dimples on single phase FAC. So these are the characteristics. You typically just go back to this one. You see this orange peel type of appearance, and for two phase you see this black shiny appearance. And this shows using a boroscope from the drum, looking down at LP evaporator tubing, you can see this two-phase black shiny appearance of the FAC. And if you look at these surfaces in detail under high power microscope, a scanning electron microscope, you'll see this appearance. And this is what we call the scallops of FAC. You have to be able to see this appearance at the higher magnification to confirm that the mechanism is FAC. This is very characteristic scallop appearance that occurs for both single and two-phase FAC. So these are those repeat situations which lead to FAC. These are all been observed numerous times. And generally what we find is that FAC results from the incorrect feed water, condensate, and LP chemistries, with the most common one being the continued use of reducing treatments. And we call this AVTR, all volatile treatment reducing. For the two-phase part, we generally find that the pH of operation is too low and not adjusted or monitored by monitoring the iron to see that the iron meets those guideline values that I showed you before. So most plants, they don't monitor. Most plants that have this mechanism, they don't monitor the feed water corrosion products, so they don't have any indicator of whether the FAC is taking place. And then, of course, you have the not challenging the status quo. Many plants that we go to operate with the same chemistry since commissioning and not using the international guidance from IAPS, which I'll show you at the end, which is freely available for you to use. And so controlling FAC in HRSGs involves three basic rules. First of all, operating with oxidizing treatment, that's the all volatile oxidizing or oxygenated treatment that control the single phase part of FAC. This means that no reducing agents should be added to an HRSG, only operating with oxidizing treatments, and then operating with an elevated pH to control the two-phase part of FAC. And sometimes, especially if you have an air-cooled condenser, then you might have to go to pH levels approaching 9.8. And we know that if you monitor the ion, like I showed you in the guidance previously, that if you operate with feed water ion of less than 2 and the drums less than 5, then this would provide you an indication that the chemistry is okay on the particular cycle. And so here, just to emphasize, these are the directions that are taken to address single phase FAC. I've already mentioned a couple of times that you have to use oxidizing environments. Do not use reducing agents or reducing treatment. And things to look for would be that what the level of oxygen is at the condensate pump or the boiler feed pumps. You want the LP and the IP drums to be ruggedly red, and that would give you an indication that you're operating on an oxidizing cycle. And when you monitor the ion, you want those to be less than 2 ppb at the feed water and less than 5 in the drums. These are the key things for single phase FAC, and these are some of the similar things for two-phase FAC. So once a plant has controlled the single phase by applying those rules, you want to ask whether the total ion matches the rule of 2 ppb in the feed water and 5 ppb in the drums. The things to look for here very clearly for you would be that the level of ion in the LP and the IP drums is greater than 20. Sometimes we see this greater than 100 ppb. You can measure the wall thickness of the tubes at the top of the LP evaporator and gradually increase the pH of the condensate and feed water towards 9.8. But as you're doing that, monitor the ion to make sure that the ion levels are coming are decreasing. So these are the simple rules for single and two-phase FAC. So the third example that I want to just mention is in the phase transition zone of the steam turbine. So these are failures and damage that occur in this phase transition zone. The phase transition zone is indicated right here. So this is a plot of the Mollier diagram, and this red line is the saturation line, and this black line here is the expansion through the turbine. So this last part here is the part that we're interested in. This is the expansion through the LP turbine. And as that expansion line crosses the saturation line, this is the area that we talk about in terms of the phase transition. So this is where the superheated steam starts to change to condensate. And this is the area where all of these failures take place, right here, because of this phase change that takes place. And these are some of the damage that we see in the blades. We sometimes see in the attachment areas when we do the NDE, these cracks that go across the engaged threads, and sometimes see deposits in the on the blades themselves. And the most important thing to look at is whether the blades and the attachment areas are pitted. You can see some good examples here of pits. And why is that important? That's important because all the failures that take place in the phase transition zone are initiated from pits on the surface. You can see right here, initiation of the failure is at a pit, and this is also initiated at a pit. All the failures that we look at are all initiated at pits on the surface, and that's because there is some inadequacy of shutdown protection. Most often we find that there's no protection. in terms of adding dehumidified air to the low pressure turbine. So these are very common, and these are the typical cycle chemistry situations which lead to phase transition zone failures. So hopefully by now you get the idea that if you allow the chemistry to operate with these CCS, then there's a good possibility that you will have these failures taking place. So the ones that are important for phase transition zone are given right here. And so you can see repetitive contamination above the steam action levels or above the shutdown limits, a lack of proper online instrumentation to measure the chemistry properly, no knowledge of the carryover or from the drums, as that goes right into the steam, and no low pressure steam turbine shutdown protection with dehumidified air, and or perhaps using some of the new chemistries like film forming substances, and so these are the main areas that we look for when we're asked to do investigation of phase transition zone failures. That was three examples of how important these repeat cycle chemistry situations are for the major failure mechanisms and damage that take place in HRSGs. So from 2008, we've collected the data associated with all the plants that we've looked at. And for each one of these forum meetings that Bob and I run, we present this information each year. And the latest international statistics were done here in May, earlier on this year in May. And this is what I'm just going to show you now. So we've looked at over 270 plants. Some of them were fossil plants, of course, but the ones we're interested in here are the combined cycle plants. So we looked at nearly 120 HRSG plants around the world and acquired the detailed data from each one of those. And these include, I think that the latest count was 19 HRSG manufacturers. But Bob might have a little different number, but it's 19 or 20 HRSG manufacturers. We tend to see the same things in each one. And these are the assessments that have been done for cycle chemistry, for failures, for FAC, etc. And so the data is on the slide right here. So this shows you the data. So these are the categories that we've been talking about. The 9 factors right here: corrosion products, online instrumentation, not challenging the status quo. These are what I've just been talking about. And in the blue column is the data from the fossil plants, and in the green column is the data from the combined cycle plants. And the numbers here represent the percentages of those units that have this repeat cycle chemistry situation as a factor in their operation. And the interesting thing is the data. The data is very similar across the two sets of plants, but the most important area that is not addressed properly around the world is the monitoring of corrosion products, the monitoring of total iron, and making sure that it reaches those guideline values that I talked to you about. The second one would be down here in terms of not having the online alarmed instrumentation that's in agreement with the IAPS standard that I'll show you in a little while. The third one is measuring drum carryover. Very often plants don't measure the carryover and therefore don't know how much of the contamination goes into the steam when there is some contamination. And then not the fourth one here is in not challenging the status quo, operating with the same chemistry, not changing the chemistry as time passes by. So these are the statistics and give us a good indication of the areas that need to be addressed. And each one of these has been addressed by IAPS in the guidelines that I will show you at the end in a couple of minutes here. And so just to finish off here, this is what we call the optimum cycle chemistry for HRSG plants. So this is bringing all of these things together. Most importantly, the chemistry should minimize the amount of iron in the cycle. And the goal here is to agree with the rule of 2 and 5. That's less than 2 ppb of total iron in the feed water, less than 5 ppb in the drums. And for the condensate and feed water treatment, making sure you do not operate with reducing agents and only operating with AVTO, and making sure that if you want to add an alkali to the low pressure system, then you follow the guidance that is available, and you have a fundamental level of instrumentation which agrees with the IAPS guidance. For the steam turbine, providing some shutdown protection and making sure that you identify these repeat cycle chemistry situations and address them. Yeah, so these are the really key things that the chemists and operators in the plant need to be aware of. So this just says that the RCCS are related to the very basics of power plant chemistry. If you identify one of these, it means that the chemistry is not optimum, and therefore the plant reliability and performance are at question. And what we find, what all the data tells us, is if you have 2 or 3 of these RCCS, then the plant will have a problem, or maybe has already has had a problem, and you need to address these and eliminate them from the operation. So the last 4 or 5 slides here I've included because Scott will provide this presentation for you, and the last 4 or 5 slides here indicate the IAPS guidelines that are available. You can see down here that the IAPS guidance is freely available and downloadable on the IAPS website to anybody in the world, and especially in Argentina, because Argentina is a member of IAPS and has been for a very long time. And so you can acquire these just by going to the website. So most of the things that I've talked about carry over from the boiler water. Instrumentation, what's the minimum level of instrumentation that you require? It's provided in here. The next 2 on volatile treatment and on phosphate provide you the guidance to operate with all volatile treatment and or phosphate and sodium hydroxide in the drums. There's a guidance for steam purity for the steam turbine, what the composition of the steam should be to minimize any damage there. This here is this one here is the guidance on how to measure corrosion products, and provides that table that I showed you before. What are the achievable levels? And then this one here shows you how to sample HP evaporators to measure the internal deposits, and provides that IAPS deposition map for you to see exactly where you are in terms of whether you need to think about chemical cleaning or not. And then there's two new guidance documents on film forming substances. This one's for HRSGs and fossil plants as well, and the one on the second page here is for industrial plants. And then there's special guidance for generator water cooling. So these are the IAPS guidance that are available for you. I think Scott also has these available if anybody wants them, but as I mentioned, you can just get them straight away on the IAPS website, right here. And I think with that, that's the last slide. So I think we have 15 or 20 minutes for anybody that has any comments or questions. And so, Scott, I think I have to stop sharing here. and come back to this and see if anybody has any comments or questions on what we've been talking about. Thank you. Thank you very much for listening.
Thanks, Barry.
Thank you, Barry.
We've got a hand raised from Jairo Romero. So if you can unmute yourself.
Where do I see that, Scott? Sorry. Okay. Okay, go ahead. Go ahead.
I'm not sure if we've. Okay, it looks like Franco Silva has a question.
Okay.
It says, what is the iron measurement you recommend? A normal operation for startups? Could you give an online measurement information?
Is that your question, Bob, or from Franco?
No, I was just reading the one from Franco.
Oh, I didn't see anything, but okay,
Yeah, it's
so,
down in the chat.
Hi, Barry. It's my question, Barry. It's about the measure. And startup measure is the most important.
yes. So Franco, I mentioned that during the presentation, we developed the levels for plants that do not cycle frequently or do not start up in a fast or elevated mode, and that was the table that I showed you. Typically, achievable levels are in the feed water at the boiler feed pump, for instance. Less than 2 ppb, and in the drums less than 5. But we recognized after this has been published, and we've been working on it now for about 3 years. I showed you the new map that we are going to publish that uses a different technique. It uses proxy techniques for measuring iron. So that means it uses turbidity or particle analysis, and those analyzers are available. You develop the trace, and then from the startup, and then you can superimpose that trace onto the map. But you're not going to be able to see a certain level of iron like you can for a normal operation. It's really whether that trace that you get would be in the green area of the map, and that would be okay. But if it's in the yellow and red, like I showed you, then you need to do something to make an improvement. And the guidance in the document provides you that guidance of what you need to do during operation and what you need to do during shutdown. It's a new concept, and I can provide you with the latest IAPS. We call it a white paper because it's not a guidance document yet, but it basically has that information in it of how to make those measurements. Let's see.
Thank you, Barry. Thank you.
Is that okay? I still don't see any chat, but
There's nothing else in the chat at this point.
okay. I didn't see that one. Okay.
Well, if there are no more, I can use the extra 10 minutes easily.
Yeah, it's okay.
Are there
Yeah,
any more
just-
questions before we
Yeah,
change?
I just wanted to mention again that that Argentina, of course, is a member of IAPS, You don't have to be a member to get these guidance documents. You can download them freely on the website. But there is an organization. It's headed by Horacio Corti at CONIA, the nuclear organization in Argentina. If there isn't any more questions, Bob, then I suggest you go ahead, and then if anybody has some at the end, we can come back to them.
Okay, very good.
Bob, just a question that what you mentioned recently. You mentioned one person from Argentina who is the let's say the leader of this other representative for this organization to Argentina. Could you repeat the name of this person?
Yes,
And also the information is in the web, isn't it?
Yeah, so I can mention it, but the name is Horacio Corti, and you can get that information from the IAPS website that I showed you. So you go to iapws.org and look for national contacts and look under Argentina. You'll see it.
Okay, I see in the chat. Okay, thank you.
Okay. Is there any more? Any? Yes. Okay, that's it from Scott. Thank you. Bob, I suggest you just go ahead.
Okay, very good. Thank you, Barry. And welcome, everyone. Let me ask first. My internet went out a little while ago, so I'm working from my phone. So let me know if the pointer on the slides isn't working properly or whatever. If so, I'll shut down my image and maybe that'll help the bandwidth. So just let me know if it's a problem or if you can't hear anything properly. So I'm going to discuss similar information the way Barry did, except this time it's going to be on pressure part failures caused by thermal transients, how we evaluate those, and what our survey history tells us about it. I'm going to also include near the end erosion of high pressure bypass valves, which is becoming more and more a problem. And so right away, my slide's not advancing. Good. Not good. There we go. Okay. Where does this information come from? Since 2008, as Barry said, we've been doing assessments of power plants. To date, there's been 68 assessments of thermal transients at combined cycle plants. This information also comes from results of post-failure root cause assessments that have been done occasionally. And they come from the proceedings of user conferences in the United States, Canada, England, Germany, Czech Republic, Netherlands, and Australia. And maybe someday we can add Argentina to that list. These thermal transient surveys have been performed on 1x1 combined cycle units, 2x1, 3x1, 4x1, and combinations of HRSGs with 2 steam turbines. We've done single shaft, multi-shaft arrangements. These plants range from 4,000 hours to 160,000 hours of operation at the time the survey was performed. And they range from 43 to 2,024 starts at the time it was performed. This group of 68 plants, some of them have had no tube failures. And there's one that has had 89 tube failures, if you can believe that. There are 23 HRSG OEMs represented in this group, consisting of vertical and horizontal gas path. recirculating evaporators and once-through steam generators, conventional HRSGs and ultra-fast startup designs, 1, 2, and 3 pressure units. Some are reheat, some are non-reheat. Some have duct burners, some do not have duct burners, stack dampers, no stack damper, and some have diverter dampers to allow the gas turbine to run in simple cycle. There are 5 gas turbine OEMs represented, both industrial and aeroderivative class of machines. There are 11 different steam turbine OEMs in this group, some condensing, most condensing, and a few non-condensing. There's seawater, river, cooling tower, and air-cooled condenser applied to these units. And there's every possible type of cycle chemistry known to man that Barry has evaluated. So some key observations from all this before we begin. The causes of HRSG tube failure are not associated with any one HRSG manufacturer. All HRSGs can run well and have no failures, and all HRSG manufacturers have units that have had failures. So it's much more to do with other issues than who built the HRSG and its specific design. Most of the causes of tube failure that were identified in 2008 continue to be a problem. Even though we know how to avoid these things, they continue. The ranking of what causes the tube failures has also not changed. So in summary to that, we know all we need to know to avoid HRSG tube failures, but many plants don't apply this knowledge. Very few of the tube failures occur due to a one-off event. As Barry mentioned with the chemistry, repeated events are generally required to cause a thermal transient driven tube failure. Very few tube failures occur due to creep damage. Creep damage is operation of the pressure part at a high temperature and at pressure for long periods of time that causes a deterioration of the material properties. That is not a big problem with HRSGs. Fatigue is the principal failure mechanism. Fatigue is generally associated with startup and shutdown of the units and sometimes with low load operation. Because fatigue is a cumulative, invisible, irreversible mechanism, if you'd identify the cause of thermal fatigue transients and eliminate those transients early in the life, you can avoid or delay the tube failure. So the actions required to break the repeated events cycle and avoid tube failure. You need to look early for symptoms of known causes of tube failure and take corrective actions promptly. If tube failure occurs, it's very important to physically remove the failure site so that you can send it to a metallurgical lab to determine the failure mechanism. After the tube failure occurs, a root cause assessment should be executed and to identify, what in the operation, design, or maintenance activities caused this tube failure or contributed to it, and then take corrective actions promptly. So the primary causes of tube failure, as I said, thermal fatigue. Thermal fatigue generally manifests itself at attemperators, HP superheater and reheater drains, to a lesser extent, LP preheater and economizer inlet sections, and excessive high pressure drum ramp rates causing cracking in the drum. So let's review some assessment results in these areas. as I mentioned a moment ago, it's important when you have a failure to remove the fracture site and send it off to the laboratory. That's the very first step in performing a root cause assessment to determine why the failure occurred and learning what you need to do to prevent future failures. In 2008, none of the sample plants had a program in place to do this. Today, only 9%. So that's an improvement, but it's still far too low, which tells us that most operators have a failure and then they do not follow through, take a sample and do the root cause assessment. So they find themselves subject to repeated failures from the same cause. The approval to take the time to keep the unit down rather than make the fastest repair possible, that discussion has to occur with upper management before failures occur. I can assure you, having been a plant manager, when the boiler is already shut down because it has a leak, no one above you in the chain of command is interested in talking about keeping it down longer. They want it back as soon as possible. So this is a process and a discussion you have to have with your boss and his boss long before the plant comes down and has a failure. All right, enough preaching about that. Very briefly, ask questions about these later if you don't understand what I'm saying. So the mechanisms that occur, accelerated creep occurs in plants that operate above 427C for sustained periods and significantly above their design temperature. As I said, creep is not a significant problem today causing failures. It occasionally occurs, but not very often. Thermal mechanical fatigue is the most common failure mechanism. And as I said, it's associated with major transients that occur mostly in startup and shutdown. Creep fatigue damage are both irreversible. They are invisible until the pressure part failure is imminent. So there's no NDE that you can do to identify that fatigue, the fatigue life of a component is nearly expended and it may fail in the near future. Excessive creep damage is rarely a problem. I've already said all this, so I'm going to move on. The two types of loading mechanisms that drive thermal fatigue most commonly are constrained differential expansion between interconnected components, which means, let's say you have two tubes connected to one upper and one lower header. One of those tubes operates at a higher or lower temperature than its neighbor. The tube that's at the different temperature will try to expand or contract compared to its neighbor, and that will create large system loads, generally at the tube to header weld. The other type of transient is global through-wall temperature gradients, as might occur in a high-pressure steam drum during heating and cooling. This also applies to thicker headers and pipes of the superheater and reheater. There is an example of constrained differential expansion. If, let's say, this tube it has water pass through it and tube 1 does not, given the height of most horizontal gas path HRSGs, this tube number 2 will shrink several centimeters. When that occurs, it'll put a bending moment on this elbow right here, which then causes stress in the well. So as that happens repeatedly, as this tube is cooled off and heated up during, more startups and shutdowns, this weld here gets bent back and forth many times. And if you recall sitting in school when you were bored, bending a paper clip repeatedly, eventually the paper clip will break. And the same thing, that's exactly what happens to the welds. This is a photograph of a typical thermal fatigue crack in a weld. It occurs at the toe of the weld in the tube material. This is very characteristic. Here's another photo of another one. So what happens in startup that causes this? One of the issues is when this business over here is a cartoon of a side view of a superheater and reheater. So this is the superheater, the hottest superheater, secondary superheater, gas flow this direction. This is an Attemperator up here, and then here's the primary superheater back here. When the gas turbine runs at high speed to purge any combustibles from the HRSG gas path, this cool air passes through these superheater tubes. And so the superheater and the reheater become an air-cooled condenser if there's water vapor inside the tubes, which in the superheater, there is always water vapor because it's communicating with the HP steam drum. This little curve over here is the calculated value of the rate of condensation that occurs in just this one row of tubes right here. And that rate of condensation peaks at 17,000 kilograms per hour. And over the 15-minute period that the purge is occurring, 3,000 kilograms of water is accumulated just in this one tube section right here. So that's enough water in this configuration to, if it's not removed, to flood up into the tubes. So that's the key difficulty during startup, particularly hot startup with the horizontal gas path HRSG, is all this water that condenses and accumulates in the superheater. This is a cartoon again of a harp where the water has been allowed to accumulate to this level. This harp's 25 meters tall. When steam flow begins, it passes first through tubes in line with these outlet nozzles. And this cartoon is depicting that movement of steam up these few tubes moves the water upwards and on into the pipework downstream. The water in these other tubes away from the nozzle does not move immediately. And so this is the mechanism that drives when these tubes are full of water and the exhaust gas is coming through there at 550 degrees, the tubes themselves are at 550 degrees. So they have expanded, this header will have moved downward several centimeters. When these tubes have steam in them, those tubes suddenly cool by 50 to 150 degrees relative to their neighbors that are still at 550. So these tubes shrink and cause the fatigue damage that we described in the previous slide. To avoid this, it's critical that the superheater, and everything I say about the superheater also applies to the reheater. This water must be drained out before steam flow is permitted to begin. Some of the design issues that have caused superheaters not to drain properly is that if the drain pipe size is too small, the water can't flow through the small pipe rapidly enough to remove all the water before the steam flow comes. In 2008, all of the steam pipes were too small on the boilers we looked at. Now, over almost 20 years, that has improved. And 60% of them now have large enough steam pipes. So people have learned from the mistake of putting drain pipes, that are too small. When there's no pressure in the boiler on a cold start, the water can only move by gravity and must flow downhill by gravity in order to be removed from the superheater. So if the drain pipes do not slope continuously downhill. If instead they go up and down, as this cartoon shows, up to the blowdown tank here, the water cannot move out, no matter what you do with the valves. In 2008, none of the drain pipes had a continuous downward slope. Now about 1/3 of them do, so there's some improvement there. This cartoon shows the blowdown tank that the water must move to elevated above the superheater lower headers. This is unfortunately a very common practice. It's gotten better from 11% to 52, where it's located low enough, but this is still a common problem. A favorite workaround for that is to add a drain valve here so that during startups from zero pressure, the water can flow by gravity into a sump. And then once pressure gets up to about 2 bar, you close this valve, and that's enough pressure now to move the water into the blowdown tank. How do we tell if the superheater is drained adequately? If you plot historical data for a startup, which has been done here, this black line is saturation temperature. This is the drain valve positions here. And the blue line, the green line and red lines are a Attemperator inlet and outlet temperature in this case. So if you see as these the gas turbine begins to fire, the steam temperatures begin to rise. They rise above saturation temperature, and then we have this sudden little quench, downward movement. This is an indication that water has passed through the Attemperator pipe and at the upper line, the superheater outlet, which means a large quantity of water passed through those. The thermocouples in the steam pipe registered that. So this is the characteristic you would see in the data to tell you that you did not drain properly before the steam flow was begun. That hasn't changed very much. In 2008, 22% of the time, superheaters were drained adequately. That's only up to 34%. So there's many more superheaters that are not being properly drained during every startup. Reheaters, it's even worse. It hangs around 40% that are draining adequately. One factor is how do you tell when to open the drain valve versus when to close the drain valve? That's best done by having a reliable means to detect whether water or condensate is in the superheater. In 2008, none of the units had any reliable means of doing that. Now 7% are able to detect it, but most do not. And this is one reason that the drainage effectiveness is so low on so many units. As I said earlier, this 3,000 kilograms of water is generated in one row of tubes. All the other tubes are generating some lesser quantity of water during the startup. So there is a lot of water to be removed that accumulates during that purge. Well, if the drains are not open during that purge to remove that water as it forms, it builds up, as we discussed, and then it takes longer to remove it after the gas turbine is fired and you want to now initiate steam flow. Only 33% of the units, 2008, actually opened the drain valves during the purge. Now, about half of the units open the drain valves during the purge. It is very important to open those drain valves early. All right. If you have any questions about drains, make a little note now, and we'll come back to them later. So now we're going to talk about Attemperators. This is a basic Attemperator system we've got for the superheater. It's similar for the reheater. So we've got the HP evaporator. Here's a steam drum. Saturated steam passes into the primary superheater, through the Attemperator, into the secondary superheater, and then out the superheater outlet. A typical control system, basic control system for an Attemperator, reads the outlet temperature of the superheater, goes through a controller that gives the spray control valve a position demand signal that then sprays the water into the steam to control this temperature. And there's generally a block valve and a flow meter for the spray water. Now, I'm only talking about HP, high pressure superheaters here. The IP superheater generally does not have an Attemperator on it, and it does not generally have problems with draining like the HP. So it's the HP superheater and the reheater that are of most concern. If you have a very basic system like this, it's just a simple feedback loop. It generally does not work very well on a combined cycle unit, particularly a larger combined cycle unit. You generally need a cascade control system that is more sophisticated and reacts more rapidly than what I've drawn here. So that level of detail is beyond the time we have today. But if you have questions about that, there's documentation we can refer you to, or we can discuss it later. So hardware problems that drive thermal fatigue associated with the Attemperators. The most common happens in over 80% of the plants we survey is leaking of spray water past the block valve. So this is a block valve. It is absolutely critical that this valve seal tightly and it be shut off at the right times to avoid water entering the steam pipe when there's no steam flow. If it leaks, when the unit shut down, the water leaks into the steam pipe, and it's very likely that it will crack the steam pipe. The upstream steam pipe and or the downstream steam pipe being too short is another problem. If the pipes are too short, the inlet pipe is too short, there's swirling and stratification and swirling in the steam entering the Attemperator that can disrupt the direction in which the sprayed water takes and cause it to impinge on the pipe wall. If the pipe is too short downstream, the water droplets that are sprayed do not have time to evaporate before they reach the downstream elbow or T or nozzle. Cracked spray nozzles or mast assemblies are a common problem. Sometimes nozzles or parts of nozzles crack and break off and go downstream. When either of these things happen, the size of droplets that are produced by the Attemperator get much larger, or maybe no droplets at all. Maybe it's just a stream of water pouring into the pipe if the mast assembly has broken off. Those things make it impossible for water not to strike the pipe wall and quench it. Many of these nozzles have springs in them and moving parts, and they can stick. The springs can come loose, causing a disruption and deterioration of the quality of the spray. Thermal liners are often installed inside the Attemperator steam pipe to prevent water contact with the pipe itself. Those liners can become distorted or cracked if water impinges on them. If the liner starts cracking, the parts of that liner can go downstream. the entire liner sometime will break loose and move downstream. And a worn spray control valve will also negatively impact the quality of the spray. These are just some quick photographs of various nozzle problems here. These are a series of fixed nozzles where the nozzle is actually missing. This is one where the nozzle's in place. Here you can see these nozzles have come out and gone downstream. This one has cracked the mast and the end come off. This one has unscrewed itself. Here's another crack in a mast. This would result in water leaking at this point and the whole mast coming off eventually. The bottom has broken off of this one. It should look like this. Instead, it's missing. There's another picture where the liner is distorted and cracked from water impinging on it. Notice the spray nozzle is not aiming downstream. It's pointing to the side, which is one of the reasons this liner is in problem. Let's talk about leaking. This is the biggest problem, leaking valves. Overspray, which means more water is sprayed into the steam than the steam thermally has the capability to evaporate. You know, there's only so much, there's a difference in temperature between the steam temperature and the water temperature. And that difference in temperature is what drives the evaporation of the water droplets. If you spray too much water, you cool the steam all the way to saturation temperature, and now no more water can evaporate. Once you've cooled the steam to 25 C above saturation temperature, if you cool it any more than 25 C superheat, we consider that overspray. You're getting too close to saturation and you probably are doing damage in the pipework. Some units are not able to spray enough water during startup to avoid exceeding the maximum permitted steam temperature limit at the outlet of the superheater. Again, how to deal with that is beyond our scope today, but some units have that issue. Unstable spray water control also can cause problems in that if a control valve is given a big step change, it will go wide open, fully open when the process doesn't actually need that much water. And then it will close and then it will open again. If those things are occurring, that will cause impingement of water on the steam pipe as well. So if we look at how do we tell that over temperature leaking and overspray are occurring, this is another data plot. This orange line is saturation temperature. The green line is inlet temperature at the attemperator. The red line is attemperator outlet temperature. This brown line is superheater outlet. So the unit starts up. The temperatures come up. The attemperator inlet and outlet thermocouples are in the same steam pipe, 12, 15 meters apart. If there's no spray, one's in front of the attemperator spray nozzle, the other is downstream. If there's no water entering the attemperator spray nozzle, those temperatures must be the same. Early in the startup, when steam flow is low, if you see a difference in inlet and outlet, where the outlet is cooler than the inlet, that's an indication that water is leaking by the spray into the spray nozzle. This is the point at which the attemperator actually comes into service. The attemperator valves here open, and we intentionally cool off the steam at the outlet. Back here, the valves are closed, so this is an indication of leaking water. Here's an indication of overspray. We put so much water in there that the outlet temperature approached saturation. You don't want to see this, and you don't want to see this. Control problems. When we have the block valve and the spray control valve, we need some kind of logic to tell those valves when to open one relative to the other. Most units use a master martyr logic that tries to protect the control valve from damage. Anytime you open a valve with high pressure on one side and low pressure on the other side, when you first open that valve, you get a very high velocity flow through a very small area between the valve seat and the valve disc. That high velocity water in that small space will erode the seating surfaces and cause the valve eventually to begin leaking. Most designers want to prevent the control valve from leaking because it's a very expensive valve to repair. If you do that, the block valve then opens, the control valve will open first so that it has no differential pressure across it. Then the block valve will open and take all the damage. It's being martyred to take the damage in order to protect the control valve. When you do that, after very few startups, the block valve is now leaking through. And now forevermore, the control valve actually has differential pressure across it because the block valve can no longer protect it. Then the control valve becomes damaged. They're both leaking at this point, and that causes the leaking that we saw in the data that then damages the pipework. If you reverse that logic and protect the block valve seat, the block valve will remain tight for a very long time, and you won't have the leaking. If the control valve leaks moderate amount during normal operation, when it closes, it doesn't do any damage because steam flow is very high and it's a benign situation. So the key takeaway here is the block valve needs to be the master and be protected from leakage. The other thing that's important to do is on startup, you want to open the block valve one time, leave the block valve open the entire time the unit's running, and then close the block valve on shutdown. You don't want the block valve opening and closing every time a temperature demand goes to zero and then comes back up. I already mentioned that the simple feedback loop for control does not work well on most HRSGs, so a cascade control system is necessary. The Attemperator should also have a minimum steam flow permissive. The Attemperator cannot possibly work if there's not enough steam flow to carry the water droplets downstream and evaporate them. So it's generally around 25% of rated steam flow before you should allow the Attemperator to come into service. A minimum exhaust gas or steam temperature permissive should be in place so that the block valve cannot open until the steam temperature and gas temperature driving that steam temperature are high enough. On a large HRSG, F-class HRSG, it'd be somewhere around 500 degrees C. If gas temperature is below that, you should not allow the Attemperator to open at all. So what does some of this look like? This is some intermittent Attemperator operation. This is a block valve position, the red line down here. The green line is control valve. You can see the block valves opening and closing every time the control valve opens and closes. This is the result in steam temperature, but the big problem is this is chewing up the seat in the block valve. This is very damaging. So we want the block valve to open once and stay open while the control valve does its thing down here. This is some more overspray. And that's the main takeaway from this slide. This is unstable operation. This can be caused by wear in the control valve, where it's so worn it's not able to control the flow. It can also be caused by sticking of the control valve or sticking in the actuator for the control valve. It could also be a loop tuning problem, but the result is very rapid changes in temperature and a lot of rapid control valve movement, the green line here, which will wear the valve out even faster. All right. If you've ever gone, if you are passing water through a coil and you're shrinking the tubes, one effect of that is to cause the cracking that we discussed and showed you pictures of earlier. Another symptom is the tubes that get quenched can be quenched so hard that they actually yield and stretch. And so when they come back to normal temperature, they're too long to fit in the space, and they do this S-shaped thing. This is a photograph of some stretched tubes. Here's another photograph of stretched tubes. If you see tubes, when you go in and inspect the boiler when it's shut down and you see tubes stretched out of line, that's an indication that you had a substantial amount of cold water pass through those tubes and cause them to yield. Here's another very gross picture of stretched tubes. The other symptom is cracking in the steam pipes. This is an Attemperator pipe. The spray nozzle is located down here, and there are 4 wells on this pipe that all 4 of these wells were cracked due to this, in this case, overspray, severe overspray for a long period of time. Here's another crack at an Attemperator nozzle right here. Leaking spray water can also cause permanent deformation and of steam pipes. This is a reheater outlet manifold, and once upon a time it was, of course, a straight pipe. Now it has like a 18-inch, a half a meter bow in it, low in the middle. And that's just from spray water leaking into this pipe during shutdown when the pipe was hot. We saw that crack already. Here's a severe case where if you put enough water in an overspray or leaking event into a superheater tube, in some cases it will pull the tube completely off the header. This is relatively rare, but can happen. It's much more likely you would end up with a fatigue crack. All right, leaking spray water. It occurs, leaking spray water falling into the tubes. In this drawing over here, this cartoon, the Attemperators are at the top of the unit. There is no drain in this pipe work to remove leaking water. So this leaking water will either flow down the pipe into this coil or backwards into this coil. 78% of the units in 2008 were configured so that could occur. Today, it's about half because the ASME code changed in 2007 to require a drain. So this has improved considerably due to that. Still far too many units. These are mostly older units, though, that have not been modified. Overspray in 2008 occurred 25% of the units. Now it's gotten worse. Almost half the units overspray during startup or shutdown or low load. Leaking spray water wasn't measured in 2008. We weren't sensitive to that issue back then. But today, 83% of the units we survey have leaking spray water. This is the number one most common damaging problem. Of all of these 68 units, 95% of them use this master control valve logic that I described, which is the wrong logic. You want master block valve logic, not master control valve logic. Some owners permit the operators to make manual changes to the Attemperator set point during operation. That's a very dangerous thing to do from a thermal transient standpoint. 2008, 22% of the units allowed the operators to manually adjust the Attemperator in service. Only 3% do that now. One of the reasons is because it did so much damage, people figured out that it was a dangerous practice. All of these things we just talked about with the Attemperators, the nozzle failures, pipe cracking, that part of that is because the Attemperators have a very difficult life. They're exposed to very high steam temperatures and intermittently exposed to cold water temperatures. So they are very, very heavy duty, stressed equipment. So it's important to inspect them regularly to look for these problems before they get so bad that they cause a tube failure or a piping failure. So it's important to have a routine hardware inspection program in place. We recommend minimum of once a year if the unit is starting and stopping frequently. 2008, only 11% had an inspection program. That's only improved to 21%. So there's still a lot of units that are just running the hardware in the Attemperator until something breaks and it becomes obvious, which is not the way you want to run your plant. Cracking in the HP drum downcomer. This is caused by excessive drum pressure ramp rate during startup or during depressurizing the unit on shutdown. Of the 68 units, about 30% of them have cracks in the drum, exceed the limit on temperature ramp rate and have cracks in the drums. This has become, as the units have gotten older, we didn't see cracking in these drums for the first 15 years of the, once a large number of HRSGs began operating. But in the last 5, 6, 7 years, as units have aged, more and more units are experiencing cracking in the HP drum, generally at the downcomer on the inside of the drum. Downcomer welds, the inside of the drum. So it's very important every time you're in that drum that the inspector look for cracking around that downcomer. If you catch it early, you can monitor it and deal with it and not have a problem. If you don't identify it early and it goes on growing and growing and you don't change the operating procedures to lower the ramp rates, that cracking can become a big expensive problem. Okay, now we will talk a moment about the HP bypass pressure control valve. Over the last, I would say, 8 or 9 years, this has become more and more common. The erosion that we see is caused by water or wet steam passing through the HP pressure control valve. When the water passes through, erodes the seating surfaces, it also erodes other parts of the valve in severe cases, the cage and the plug. When the seating surface damage gets bad enough, the valve begins to leak steam. Most of the time, there is a carbon steel pipe downstream of the pressure control valve. When this superheated steam starts leaking through the valve during operation, it overheats that carbon steel pipe. if you find yourself in that situation, the only safe alternative is to open the pressure control valve, manually open the pressure control valve to its minimum operating position. And that will allow the superheater downstream to automatically come into service and cool the downstream pipe work. You absolutely should not manually open the superheater spray valve to try to cool the downstream pipe work with the pressure control valve closed. If you do that, you guarantee to crack pipe work downstream of the superheater. It's very uncomfortable, and it's a pretty big efficiency hit, heat rate hit, in order to operate with the pressure, with the bypass, HP bypass open, even at its minimum position. But that's the only safe way to operate the unit if the leakage gets high enough to overheat that downstream pipe. And you have to just run that way until you can shut the unit down and repair the pressure control valve. There's some photographs of eroded pressure control valves. This problem is not specific to any valve manufacturer. They all have this issue if wet steam or water is allowed to pass through the valve. This is not melted. When they pull this out, the plant people said, geez, my valve melted. It did not melt. This is erosion, this severe, that chewed up this thing. This used to be the seating surface up here once upon a time. This is the body of the plug where it's around. This is a different manufacturer, but it had a cage similar to this surrounding this plug when it was in service. And these dimples are erosion caused by water mixed with steam coming through the holes in the cage and impinging on the outside of the plug. This one's seating surface was also damaged, but not as badly as this one. This can occur, the one on the right here, this occurred after like 2 startups on this unit. This happened every time they'd overhaul the valve, they'd start up twice and it would go back to leaking. And then, a couple months later, they would shut down and find this in there again. Sometimes it happens slowly. Sometimes it happens very fast. So where does the water come from? It can come from undrained condensate in the HP superheater. All this discussion we had about draining the superheater. If you don't drain the superheater, and you generally initiate steam flow by opening the HP bypass. You either open the HP bypass or you open a HP sky vent, startup vent. If you open the HP bypass, all of that water, that 3,000 kilograms of water, plus more, ends up traveling with the steam through the HP bypass valve. So that's one way to damage the valve very rapidly. Leaking Attemperator spray water can also find its way to the HP bypass valve. If you have a final Attemperator, which is an Attemperator that's located at the outlet of the HP superheater, leaking spray water at that location can also find its way through the bypass valve. And the more insidious one is undrainable water trapped in steam pipes. Steam pipes over time, steam pipes and their support system may move and create low points that where no drain is located. The pipes can deform, like the picture I showed you of the reheater outlet pipe that actually took a permanent bow and created an undrained low spot, or the hanger system may cause locations of the pipe to be up or down relative to where they were designed to be. So there may be water in that steam pipe work that finds its way through the valve that you don't even know is there. And finally, condensate must form in a steam pipe as steam heats the pipe up from cold to hot. If that condensate is not drained away before the HP bypass is open, that condensate will go through the valve, causing erosion. I want to go through a couple of pipe schemes to demonstrate how that happens on many units. Let's say this is a 2x1 combined cycle plant. So I'm only showing steam from one HRSG here. It's coming from the superheater. This is the branch to the bypass valve here. So the steam would flow this way. This is the isolation valve to the common steam header. And then our steam turbine is over here. And here we have warming drains just in front of the steam turbine. Now, what I'm not showing is another HRSG steam pipe coming in over here, and it would be here. So this is just one of the two. During a cold start, steam turbine is cold, it's shut down. We're starting this boiler. We would have the bypass valve closed. We would have this isolation valve open. There's a little drain here with a trap on it, or a level controlled small bore drain here. We have some relatively large warming drains here. These warming drains are open. This isolation valve is open. Steam flow from the boiler as it begins flows this way, warming this pipe, warming the main steam header, and exiting through these warming drains. So we've got a good flow path to warm all this pipe work. Pipe's good. By the time all of this is hot enough to, because this pipe is warming, we reach a point where we can open this bypass and have this section of pipe superheated so that we get no water into the valve. And this is the data plot of that occurring. So the unit fires here. This is gas turbine exhaust. So the unit fires here. This blue line is superheater outlet. The green line, this green line is the temperature here at this drain. The blue line is this temperature, and the green line is this temperature. So they both follow saturation temperature as that pipe is warming, but at some point here, they become superheated. The bypass opens here. By the time the bypass opens, there's 103 degrees superheat in the steam it's receiving. So there's no problem with this cold lead start. The first unit start cold, no problem at all. And that's because we have this substantial warming flow through all that pipe work, in particular through this section of pipe work. Now let's do a hot start up, same pipe work. Now in the hot start, we may have this valve closed because the turbines may be on or it's already hot. So we may have this valve closed and we want to be on the bypass quickly to get the HRSG going. But this section, this temperature and this temperature during the hot start, they're already superheated. Those are the same temperatures. So when the bypass opens, again, we've got 82C of superheat. So there's no problem during the hot start with the bypass. primarily because that critical pipe work did not need to be heated. It was already hot and dry. Now we're going to do a cold lag start. This unit is going to be the second one to start. Steam turbine is already on. This other boiler that we're not showing over here is providing steam to operate the steam turbine. Our isolation valve is closed. Our bypass is closed. This line is cold. The only flow path we have is this 3.8 centimeter drain. This is not a warming drain. One, it's too small, and two, it's controlled by level devices in this drain pot, and it only opens to let out water. It does not open to remove steam. So what's the data look like? Gas turbine again fires here. Superheater outlet and downstream pipe temperature. They're following saturation. There's no steam flow in those pipes in order to warm them. So the superheater outlet begins to get some superheat, but the steam pipe temperature downstream of the bypass T remains cold and at saturation. So when the bypass opens, there's no superheat, and the condensate that has been forming in this pipe is drawn into the valve at this point. The pipe work immediately begins to heat up once the flow path is established by opening the bypass. So it's almost always the cold lag start that causes the erosion in the bypass valve. So a remedy for this is it may be necessary in a unit configured this way to increase the size of this drain on the order of the size of these drains so that we get a substantial steam flow during this lag startup to warm this bit of pipe here so that we have superheated steam when we open this valve. So the basic actions to avoid bypass valve erosion: make sure you drain the HP superheater early in the startup, both for the superheater's sake and for the HP bypass sake. Ensure that your attemperators are not leaking. You need to review the DCS data to determine if you have superheat at the pressure control valve when it's opened. If you look in the manuals for the suppliers of the pressure control valves, you will find they say you must have some superheat before opening the valve. They don't generally give you specify how much superheat. Discussions with the designers of these valves, it looks as though something on the order of 25 degrees C superheat is sufficient to protect the valve from damage. You may have to install additional thermocouples on the pipe work going in front of upstream of the bypass valve in order to get sufficient steam temperature information to make this decision about when to open. One final thought is avoid using the HP bypass when the boiler is not being fired. Not all HRSGs do this, but some HRSGs, if you open the bypass when the gas turbine is not firing in order to depressurize the unit, for example, to expedite and cool it more rapidly, that can cause condensation in the superheater, which will then be pulled through the bypass valve and cause this erosion. So if you're going to depressurize the unit or force cool the unit using the bypass, HP bypass, you need to investigate the pipe and steam temperatures upstream of the bypass to ensure that you're not generating condensate and then moving it through the bypass. This is some data of a unit that did just that. So the red line's a bypass position. The unit shuts down here. This is exhaust temperature. So the unit is down. This is superheater outlet temperature. Bypass opens, superheater outlet temperature is cooling off, and in only about 40 minutes later, superheater outlet is now at saturation temperature, the black line. From here on, we're just pulling water that we're generating in the superheater through the bypass. You don't want this to happen. Okay, that's the presentation. Let's I'm going to end, well, I'm going to leave this open. Do we have any questions?
There's nothing in the chat right now, Bob, but if anybody has any questions, please either put them in the chat or just unmute yourself and ask away.
No question for me. Well, thank you. Well, if there's no questions, I want to use some minute to thank you for organizing and giving this information and well making this Argentinian forum possible. We are very proud of having this meeting and all the participants that could make it an effort to participate. So, well, I hope we can take more of these events, these meetings to, well, share knowledge. We are very thankful for having this, making this possible.
Thank you, Franco. I think there was a lot of interest. We had 50 people stay to the end of two quite long presentations, so that was very good. And I think Bob and I look upon it as the introductory meeting here with you. We'd like very much to keep in contact with you, and I think from my point of view and Bob's point of view, I think if you have any questions, Bob, they can always just contact us at any time.
That's correct.
And Franco, if any of your 50 colleagues there have any questions about anything, I know when it's in a different language, it's sometimes a little difficult to comprehend. But maybe you think about some questions afterwards, and you can raise them with us, and you can always. You can always suggest other topics maybe that we didn't cover today. We tried to highlight the major things that happen in HRSGs around the world, and maybe if you have some other thoughts about something that you'd like a little bit more detail on, then you can either come back to Bob or myself or to Scott, and just suggest that, and we're very open to that. And as I mentioned, I don't know how many chemists you have in the group there, but you know the chemists should be aware that the IAPS organization is the leading organization for water and steam in the world, and particularly for guidelines in combined cycle plants. And you can get any of the information there freely available, not only because Argentina is a member of IAPS, but because we do that for every country in the world, you know. And so if you have any questions, I think just please get back to us. We'd be very pleased about that.
Okay, Barry, Bob,
Thank you.
thank you very much.
Thank you.
Thank you.
I want to say thank you to Barry, Bob, and Scott. I want to say some words in Spanish. Bueno, muchas gracias a todos los que participaron del foro. Gracias por la paciencia también. La idea es que sea el primero de muchos encuentros. Organizar este tipo de eventos también presenciales, esperemos el año que viene. Pero primero haciendo un relevamiento de las problemáticas e inquietudes de cada sitio y poder armar en conjunto con el grupo de químicos de Pampa un poco la agenda y que sea beneficioso para todos. Así que en nombre de todos les agradecemos.
Gracias, Franco.
Gracias, Franco,
gracias
muy
por
bueno
participar,
todo.
por el tiempo.
Chao,
Les agradezco.
gracias.
Espero que sea de
Thank
utilidad.
you.
Thank you.
Gracias.
Adios.
Gracias, hasta luego.
Gracias.
Hasta luego.
Thank you, Barry. Thank you, Bob, for the time, for the work.
Thank you, Barry. Thank you, Bob.
Gracias a todos. Hasta luego.
Thank you. Good. The CC Scott even translates it in Spanish. It's good.
Yeah, I saw that myself. It was great. So
That was amazing.
just before everybody signs off, we'll be sending out a link to the recording and a transcription of the presentations as well to all the attendees, and feel free to share that with anyone in your organization. Thanks to both Francos for reaching out to all the turbine users in Argentina, and bringing such an impressive number of folks to today's presentations. Thanks so much.
Okay. Well, thank you for participating in this, for the information and the work, and maybe I can send you the addresses of every people who joined here. I think you have this by the WebEx page, but also I can resend you this information to share
Okay.
for other events or everything.
Great.
Thank you for the time again, and well, I expect the presentation.
Yeah, we'll keep in touch with you. Maybe you can come to Brisbane.